in order to experience correctly the difference between the word matrix and the view matrix, we add some sort of minimal interaction. So again, if you go into the utils, you will see that there is an interaction function. We want to register this interaction function so that by pressing keys you can move the camera around. So concerning index.html, it doesn't change, because everything is exactly the same. In drawing, we have to start making some modification that we will use from this point on. So the first thing that we need to do is to create some camera parameters. Instead of coding them directly inside the function that creates the camera, we want to parameterize this creation. So we create var camera x with exactly the same value that we put inside the function before. So here is 0, here is going to be 1, and this is cy, and this is cx. Then we also want an elevation parameters, which is 0.0, and another one which is angle, and we put the minus 30 degrees, we put there. We also need another variable, we call it delta, which is the delta of movement that happens each time we press a key. 0.1 for the dimension of our current frustum are enough. Consider that if you draw a bigger object, you need to change this parameter. 0.1 as a delta can mean that you are not able to move enough during your interaction. So another big change that we want to make, since now we don't have just one main cycle which is interpreted linearly, more or less linearly, but there are sub-functions that are called, we need to have vertex position handle and matrix position handle as global variables. So we put something like this, and we put them, let's say, here is an okay. So we have them here, and we need to remove the var, otherwise they are considered new, even with the same name, but different variables, and only for this scope. Okay. Now, first thing we want to do, for example here, is to insert the function we have just here. So interaction function. We copy all the function, brackets included, and we put here, of course, inside, so for example here, okay, and the function is pretty simple. There is a quick interpretation of the element that causes the function to be raised, and depending on which is the code, the ASCII code of the key, E is the event that raised the function. There is a key code associated to it. If this code is equal to this value in ASCII coding, do something. Move the delta. So those are the code for right arrows, up arrow, the add and the subtract button, A, D, W, S. Then we register attached to the window, which is the window in which we load the cube, this function. So when the event key up is raised, the event listener executes the function, and the function decodes the code of the key. Pretty straightforward. This is called an immediately invoked function, which is a feature of JavaScript. So you can define a function and put its return value somewhere. Okay. Then the computation matrix, the difference is between the code that we previously coded and now is that we need a main rendering cycle, meaning what? That we cannot just draw once our cube as in the past. We need to draw and draw and draw again up to the lifetime of our code the cube. Otherwise we don't see any interaction. So logically we draw the cube, we wait for a key to be pressed. If the key is pressed, some value changes. The position of the camera changes in the space. So the next rendering time, the cube will be drawn in a slight different position. So we need to introduce this complication. For doing this, we cannot compute our matrices as we did here just once. We need to compute each rendering cycle our matrices. This is why what we need now is a compute matrix function. No parameters to be passed, and we move here everything we did for the matrices. Okay. Well, as I told you before, maybe we can leave for, let's say, performance sake, perspective matrix outside. We can just compute it once, so we don't need to calculate the frustum each cycle. We can leave it here. But the view matrix is indeed what we change each time. And of course, now it is parameterized. It is Cx, Cy, Cz, elevation, and angle. And projection matrix is again recomputed each time, because even if perspective doesn't change, view matrix indeed does change. Okay. And since it is not, probably I prefer to move this function just for better availability here. Okay. And then we need also a function which is called draw scene, which is going to be our main rendering cycle. Something that is drawn and drawn and drawn again until we close the window. Okay. So the first thing we need to do each time we enter the draw scene cycle is to call compute matrix. We need to compute matrix again. Then everything we did before, So the passing of the matrix, the passing of the data needs to be moved in the rendering cycle. We left outside all the operation that can be performed just once.
Last time.
Okay. The using of a program, unless we want to change the shader during the lifetime execution, can be left outside the main rendering cycle just once. Since we don't have any other input handles to be collected, we can collect them just once. All those functions can be left outside the rendering cycle. But what we need to call in the main is the init interaction, otherwise interaction is not going to be initialized, and the draw scene. So once the main execution reaches this point, the draw scene, the rendering cycle, is called the first time, and from that moment on everything happens basically in the sub-function. The last thing we need to do to make it recursive is here we need to call this window dot request animation frame draw scene. There are a couple of times to make draw scene a loop. The first one is to simply call draw scene at the end of draw scene. But in this case, we don't have a synchronization between the moment in which the monitor sends a signal, the vsync signal, so it's ready to visualize a new frame, and the moment the frame is created. This is what this function prevents. Each time a new frame can be requested by the browser, call draw scene. So the loop exists, but we don't have to deal with things like synchronization by calling them. So let's see the effect, if there are no errors. You see, I am pressing keys, and now the camera is moving around. The object is still, it's just the camera, it is the viewpoint that is changing. Okay. So to exactly see which is the difference between the view matrix and the world matrix, we are going to animate something about the cube. We are going to move the cube around during the execution. We need to add a world matrix. So up to here we can add a world, maybe, I don't know, maybe at the end. We can add a world matrix. This matrix is going to be in charge of defining where the cube and which dimension the cube has inside the world. Okay. And as we created parameters for the camera, we have to create cube parameters. Okay. So we have to we want to put, for example, our cube at -1, so we have 2 units distance between the cube and the observer. We also need to specify the rotation of the cube along all the axes, expressed initially as just zeros. And also we want to modify the scale of the cube, so cube S, but since it is proportional, we don't need any parameters more. Also a flag, which is going to be a boolean really, but there is no big difference between a boolean or a 0-1 variable, so we just put the flag to 0 and we will see which is the purpose of this. In order to animate, we have to interact with the clock of the machine, so we use this other variable, last update time, which is a new date dot get time. We go to the clock and we get the time in milliseconds. That's it. It's called last update time because we want to make we want the cube to rotate around and scale big and small, and we want to do that at a speed which is coherent with the speed of your machine. That's why we are contacting the clock. And since we want to animate, we create a function which is called animate. Okay, this function is not important, it's just a cosmetic effect, so even if it's not so clear, don't worry. We are making a difference between the current time when the function is called and the previous time the function was called. And using this delta, we define how much the cube rotates or has been scaled. So current time is exactly equal to a new date get time. So if something changes, so we have a last update time, do things, and the things we need to do are define a new delta, which is the amount of modification to the cube that we want. 30 frames per second, the delta between current time and last update time. Okay, normalized in seconds. Okay, and then no, I need to take the original variables, so I can go here. Okay, so we modify rotation along the axis using the delta we just computed. Plus, minus, put anything you like to see if you want to see different results. About the scale, since we don't want that the cube becomes bigger so much that we don't see it, or so small that we cannot see it, we have to put a range. That's why we have a flag. So if flag is equal to 0, then we want the cube to grow. And so cube S is going to be equal to delta C, not too much, okay. else. Otherwise, if the flag is equal to 1, we'll reduce the cube. Okay, but then if the cube S, so the dimension of the cube, is bigger than 1.5 times its original size, that flag becomes 1. So, okay, it's too big, now shrink it. Else if, it's better, otherwise the logic doesn't hold. If cube S instead is going too small, so let's say less than half its original size, it's better to do equal, but not really less than, okay, then flag becomes 0. It's a bit complicated, but just in order to do something. At this point, we can create our word matrix. So word matrix is going to be equal to utils dot make word matrix. Okay. Make word matrix requires the position in the space for the object, its rotation along the main axis, and a scale value for it. That's what we are going to provide, the function, and so we put cube dx. And then cube S. So each time the function animate is called, a new matrix, a new word matrix for our cube is computed. Last thing, but not least, is to update. Last update time becomes now equal to current time. Otherwise, the delta is not properly computed. Okay. Maybe this animate function too, I can move it after the init in order to have everything close. So, view matrix doesn't change, but there are changes here. Projection matrix is going to change because now we have one more element in the final stack. So projection matrix is going to be equal to view matrix multiplied by the word matrix. Okay. And then again, projection matrix is going to be perspective matrix, but multiplied by the previous value of projection matrix. Okay. Another thing we need to do is, before computing matrix, call animate. Okay. There are mistakes. Okay. Unexpected token. Yeah, thanks. Okay, and that's the effect. So when it becomes too big, it shrinks, and again, and repeat this after them. Of course, I can move also the camera around, and now you see how the two matrices, the two different matrices, are interacting one the other. I'm not moving the object is moving by itself, I'm just moving the camera around. So by combining those three matrices, the world, the view, the perspective, I obtain the projection of the object inside the 3D. And that's it. Now, let's change a little bit the things. Now we don't want any longer to just have the wireframe. We want to have an object which is complete. Okay, so how to do that? This is what we want to achieve. First thing, we change the definition of the cube. We don't only have vertices now, we also need to define triangles. In order to avoid the problem of multiple of redundant vertex definition, a technique that allows you to refer to a given vertex by a value is used. It is the index. We add another buffer, which is the index buffer, and you see that a triangle, for example, each face of the cube is defined by two triangles. In 3D graphics, there are basically triangles or quads, but even the quads are not rendered as they are. Usually they are downgraded to triangles. So in this case, let's look at this triangle here. It is made by 5, 1, and 3 vertices. With 1, I'm referring to the vertex using those coordinates. With 3, the vertex having those coordinates, and with 5, to those. And the order matters. We will see that it is important because the order of the vertices for a face defines the direction of the normal to that surface, and the normals tells us if the face is facing us or the opposite. So the order is pretty important. Now we have to change, in order to achieve this, the definition we had before was okay because we just need lines, but since now we need faces and we want to avoid the replication of the information about the vertex, then we have to use these indexes. And indexes can be seen in cube definition 2. We still have 24 vertices for now, but those vertices are used for drawing triangles. So 3 numbers here define one vertex, 3 numbers here define one face. There is an upgrade. And what we want to use for drawing are those information, not the information before. The information before still are somewhere on the memory of the graphic adapter, but we want to use those values for using those data. Okay, so the first thing that we need to do is to change the cube definition and use cube definition 2 if we want to see the faces. We go to the proper folder, utils folder, and we copy and code cube definition 2. Okay, you can leave the old one, which is not used now, without any problems. Okay. Now, since we have 2 different buffer objects, the binding of those buffers, the function we call bind buffer, becomes more meaningful than before. And we need to have a couple of globals, of new globals, which are the VBO and the IBO, vertex buffer object, index buffer object. And when we create the VBO, we remove buffer because it's already defined. Instead, we have to add here IBO as a new buffer created exactly as before. Then we bind it. If we simply buffer data, if we simply call buffer data now, the data are buffered inside the VBO because it's the last binded and it's going to create an error. So we have again to call the bind buffer to this new buffer. First of all, it is EBO. Okay, it's no longer just an array buffer, but it is an element. It's a different kind of array. Element array buffer. Okay, and so we can now buffer data inside. It's a different kind because it's different the user. We no longer have values that we want to use directly, but we have element referring to values. That's why we changed the definition of the buffer. So it is an element array buffer, and we need to create a new, this time unsigned int 16-bit depth array. And we move inside index, which is this array here. Again, we need everything for a static draw. We don't change anything inside that. Okay. So we have two buffers. Strangely enough, the shader doesn't change. If we provide the proper amount of data to the shader doesn't change. That's why we are experiencing in JavaScript and in GLSL, even if at your exam only the GLSL part is required, not the JavaScript one. But a shader cannot exist by its own. It depends too much from the client code calling and using it. So that's why you need to see the interaction between the client code and the shaders code. Otherwise, the shaders is, I don't want to say meaningless, but less, with less importance. You see, the important thing now is to see that the shaders per se doesn't change. It doesn't changes instead the draw function. The draw scene changes a little bit. Okay, we send the matrix, and that's something that we don't need to change. But now we need to bind some buffers before. We have to copy the lines we have here. First this one. Okay, and then the other one. Because we want that the data that vertex attribute pointer pass are those inside the VBO, not the other buffer. And since we have more than one buffer, it is important that before we call a function for communicating, we are sure that the buffer from which the data are taken is exactly the one that we want. Okay, so gl dot draw elements, and the elements are going to be gl triangles. We send them a number which is the length of indices. We are going to be gl.unsigned short. There is a 0 in the end because there are no offset. We will see things about offset later. Okay. Of course, we remove this other one, this other function, because we are not going to draw from an array, we are going to draw from the elements. Let's see what happens. Okay, it's a little bit big, but now we have triangles instead of lines. The last thing I want to show you before closing today's lesson is the concept with which I started the lesson. We call them vertices, but it's an improper definition. Why? Because we can have more elements stored per vertex, and that's define a vertex format. Let's see if I can be clearer than this. Okay, so if before we had that for each vertex just an x, y, and a z was required, if we want to have, for example, a direction for the face, next lesson we will see normals for now, but let's say that we want to couple a color to a vertex. Well, that's what happened. You see at the bottom here. The first three values are the x, the y, and the z for the position of the vertex. The other values are the RGB component of the color for that vertex. So now, for each of those entity that we call vertex, we have 6 values, not just 3. That's why vertex is diminutive for it. Okay, so to see how this works, let's switch back here. Let's copy definition 3 from utils. We now need cube definition 3. And of course, we need to change an index. If we look at the definition, now you see that there are 3 more columns for each row. This is the color of vertex 0, this is the color of vertex 1, and so on. Indexes doesn't change. We just added more values per vertex. There is another thing we need to change in drawing. At the very beginning, we now have not only a vertex position handle, not only a matrix, but we need also a color. So vertex color handle. We need another parameters here. This shader doesn't work any longer because it does only have 2 input values, the position and the matrix, but we need to add to it also a third one, the color. Okay. So we put this part here, in which we have one more element. And because of this, we duplicate this line. I don't remember our point color, vertex color handle, vertex color handle. So vertex color handle is again an attribute location in program, but not pos, instead color. Okay, so we have another input value for the shader to pass. And so in the draw function, we have to specify this. Okay. Vertex position handle, we pass 3 here. What changes is now this thing. Okay, I'm specifying that the buffer in which there are all the information about the vertex, both the position and both the color, is composed, our vertex format is composed by 6 floating values, and each floating value is of the size of 4 bytes. That's why we need to put 4 per 6. We are just specifying this. Otherwise, it is not able, WebGL is not able to decode the information inside the blob of data. As we enable this one, we have to enable just after also the vertex color handle. And again, we pass with more or less the same line is not changes this. Okay. GL float false, and again we have a change here, meaning that even if we define a row of 6 floating value, start from 0 position of those 6 out of those 6 and take 3. So the 0, 1 and 2 of this subarray are used for the coordinates. Then a similar row, which is similar, this is of 6 floating values, but now start from position 3 and take the 3, 4 and 5th values, because again there are 3, but those 3 values, send them to color handle. We have the blob of data, all the data about the vertices. We divide this blob in 6 element subarrays. We take from these 6 subarrays the first 3 for position and the second 3 for color. Everything else remains basically the same. We just added something more. And we have a colored cube. As you may see, there is a strangeness. We are seeing both the faces are not sorted correctly. You see the yellow, for example. You are not able to see which is the face, and you see through. There are some oddities. That's why we didn't activate the depth test based on the Z buffer. WebGL is not able to tell which is the face closer, the pixel closer to the looker. Just take one. It is a sort of Z fighting. So if we want to avoid the Z fighting, we have just to enable the GL test at any time here. Probably better before the draw scene, just for logic. No. GL.enable GL.test. We don't have to implement ourselves the sorting of the set, which is something that you may have to do if you want to correctly apply the alpha of the textures to your own object, because in that case it's very difficult for the standard depth test function to predict correctly what you want to see and what is instead to be considered transparent or semi-transparent. But for now, you're lucky enough, you don't have to do that. So, and now the cube is more like a cube. One last thing I want to show you, and then we can end the lesson, is how it is, what is doing exactly. Because, you know, we just expressed a color for a vertex, for each of the vertex, how it is that all the face becomes colored. You can go, for example, in the cube definition tree inside your folder, and let's see this one. We put it, for example, to another color, totally random. Let's do a couple of times. Okay. Now, somewhere, if you are lucky enough to go to the right face, you see that there is an interpolation. And that's an important concept, because the color of one vertex is interpolated toward the color of the other adjacent or next vertex. It's quite important to know, because for now we are using colors which are harmless. But when in those positions we code the normals to the vertex, that becomes important to know that we can obtain the smooth shading, because there is an interpolation along the surface of the direction of the normal. So that's how it happens. There is an interpolation along the line. Okay, so for today we just finished basically what we started last time, which is the basics of WebGL. We started from simple 2D element and we go up to a 3D object. For looking at the 3D object, you need to multiply together three matrices: the world matrix, the view matrix, and final projection frustum matrix. And the other concept, which is quite important, at what we consider a vertex for a polygonal object, is an entity that can store more values than just the position. That's it for today. Thanks.